I want to make a video of the factoring practice handout that you're given in class. You'll be given this in class tomorrow. I'm sending the video out to you tonight. The substitute will also show this in class tomorrow after you have time to practice some of these and figure out which ones you need help on. So and what I did was I jotted down little hints for some of them that should help you. So for the first one, you have to factor each one completely. For number one, it says r squared plus 15r plus 50. Since you have a quadratic trinomial, the first thing you're going to do is see if you can find two numbers that multiply to 50 and add to 15, because if the coefficient is 1, you can factor them knowing that two terms need to multiply to c and add to b in the general equation ax squared plus bx plus c. If a is 1, again, the two terms need to multiply to c, the constant term, and add to b, the coefficient for the linear term. And so we need two numbers that multiply to 50 and add to 15. Those two numbers are 10 and 5. So r squared plus 15r plus 50 factors very easily to r plus 10 times r plus 5. Again, using the same reasoning that you used for number 1 for number 2. If you have a coefficient of 1, then you need to figure out what b is, the coefficient for the linear term, and what c is, the constant term. Since the coefficient for the linear term is -1, the two numbers that you're looking for have to add to -1. And since the constant term is -30, those two numbers also need to multiply to -30. You'll find after thinking about the factors that multiply to -30 that you come up with -6 and 5 as your two numbers. So n squared minus n minus 30 factors very easily to n minus 6 times n plus 5. Moving on to number 3, x squared plus 14x plus 40. You're going to use the same reasoning. The two numbers need to multiply to 40, add to 14. You'll find that those two numbers are 10 and 4. So you get x squared plus 14x plus 40's factors very easily to x plus 10 times x plus 4. You can use the same reasoning for number 4. The two numbers that you're going to use need to multiply to -6 and add to +1. You get x squared plus x minus 6 factors very easily to the two factors x plus 3 times x minus 2. For number 5, same reasoning. They need to the two numbers need to multiply to 40 and add to 13. Those two numbers are 8 and 5. So you get the two factors x plus 8 times x plus 5. One of the factors is x plus 8, the other factor is x plus 5. For number 6, same reasoning. Multiply to 40, add to -14. X minus 10 times x minus 4. Those are your two factors multiplied together. Now, if we look at number 7 is a little more math, but it's not really that tough. All you have to do is I put a hint down to use prime factorization and factor the greatest common factor out of each term. For number 7, if you look at 60 factors to 2 times 3 times 2 times 5 times m cubed. So I wrote those down, and I wrote them in order with the same factors next to each other, starting from the lowest number up to the highest number. So I have 2 times 2 times 3 times 5 times m's cubed, which is really m times n times n. For the next term, we have 354 m squared, which factors to 2 times 3 times 59 times m times m. So I wrote that down. I put my plus sign. I continued with the same operation. 2 times 3 times 59 times m squared, which is times m times m. For 270m, that factors to 3 times 3 times 3 times 2 times 5. I should have put it in the correct order. I didn't, but it really doesn't matter. 3 times 3 times 3 times 2 times 5 times m. If I look at the factors in the first term, the factors in the second term, and the factors in the third term, I can take a 2, a 3, and an m out of each term, multiply those together, you get 6m. That's your greatest common factor. you take that greatest common factor out of each term, leaving you with what's remaining for each term multiplied together. So in the first term, for instance, you have a 5 remaining, and you have an m to the third power remaining. When you multiply those, you have a 2, a 5, and an m cubed. Multiply those together. Let me step back a second. You factored out 2 times 3 times m, you're left with 2 times 5 times m squared, which becomes 10m squared. Sorry about that jumble, I was trying to do it in my head. Now, for the next one, you factor a 2 times 3 times m out, you're left with 59 times m. And for the final term, you factor out a 2 times 3 times m, you're left with 3 times 3 times 5, which is 45. So the final result, when you factor this, when you factor 60m cubed plus 354m squared plus 270m, you are left with 6m times the quantity 10m squared plus 59m plus 45. Sorry about the mix-up over here with the factoring. All right, moving on to the next one. For number 8, you have 18p squared plus 16p minus 40. Now, you can do this without factoring a 2 out of each one, but then you're going to have to do that at the end anyway. So what I did was I immediately looked at this, noticed they were all even. I factored 2 out of each term. That left me with 2 times the quantity 9p squared plus 8p minus 20. This time I used factoring by grouping. And this time, what you're going to do, the whole idea is you're going to break up your linear term, and you need 2 numbers now that multiply not just to negative 20, but 9 times negative 20, or a times c, which in this case is negative 180. So you need 2 numbers that multiply to negative 180 and add to positive 8. I made a little chart up here that has the factors that multiply to 180, and I stopped when I got to the right ones, knowing that I'm going to use 10 and 18, which are separated by 8. I'll make 18 the positive number, and I'll make 10 the negative number. That way they multiply to negative 180, and they add to positive 8. So I'm going to break up the middle term. Instead of writing 9p squared plus 8p minus 20, I'll write 9p squared minus 10p plus 18p, which is the same as 8p in value, minus 20. I put parentheses around the first 2 terms. I leave my addition sign. I put parentheses around my last 2 terms. Then I factor a 9 out of the first 2. I'm left with 9p minus 10. I factor a p out of the first 2. I'm left with 9p minus 10. And then I factor a 2 out of the second set of terms, and I'm left with 9p minus 10. You have to be left with the same quantities inside the parentheses, the same 2 terms, 9p minus 10, 9p minus 10. So that becomes one of your factors, 9p minus 10. And then the remaining term that you factored out of the first one, the operation, and the term that you factored out of the second set gives you p plus 2. So your 2 factors are 9p minus 10, the stuff inside the parentheses, and p plus 2, the stuff outside the parentheses. Don't forget that you initially factored a 2 out, leaving you with 18p squared plus 16p minus 40 factors to 2 times p plus 2 times 9p minus 10. Let's move on to number 9. For number 9, what you're going to do is you're going to use, first you're going to factor the 2 out of each term, out of 50k squared and out of 18, leaving you with 2 times the quantity 25k squared minus 9. And then you have to be able to notice this, and this means knowing your squares. You have to notice that 25k squared is a perfect square and 9 is a perfect square, knowing that when you have the difference of 2 perfect squares, assume the first square root is a and the second square root is b, keeping positive values for that. You get that a in this case equals the square root of 25k squared, which is 5k, and the square root of 9 is 3. So you have now, instead of 25k squared minus 9, you're going to use the fact that the difference of perfect squares becomes a plus b times a minus b. So you get 2 times 5k plus 3 times 5k minus 3, because you initially factored a 2 out. what we did was we set a equal to 5k and b equal to 3. For number 10, you're going to use the addition of perfect cubes. And in this case, you know that you're going to use the general factoring of, if you have a cubed plus b cubed, that becomes a plus b times the quantity a squared minus ab plus b squared. In this one, 64a cubed, if you take the cube root of it, you get 4a. And if you have 1 and you take the cube root of it, you get 1. Taking 4a for a and substituting it in for a in the general equation, taking b equals 1, substituting the 1 for b anywhere in the general equation, you can rewrite that. Instead of a plus b times a squared minus ab plus b squared, you can rewrite that as 4a plus 1 times the quantity 16a squared minus 4a plus 1. For number 11, you're going to use the same logic, only you have the difference of perfect squares. So instead of using a plus b times a squared minus ab plus b squared, you're going to use the general equation for difference of perfect cubes, that should say cubes, a minus b times a squared plus ab plus b squared, and you get, when you rewrite it using a equals 2m and b equals 5, 2m minus 5 times the quantity 4m squared plus 10m plus 25. For number 12, you're going to factor 4 out of each term. Then you have the difference of perfect cubes, where a equals 5x, b equals 3. Substituting those into the general equation, you get 4 that you factored out times the quantity 5x minus 3 times 25x squared plus 15x plus 9. For number 13, you're going to factor out of a 3 and then use the sum of perfect cubes, where a equals, after you factor the 3 out, you get 3 times the quantity 8x cubed plus 125, where a equals 2x, that's the cube root of 8x cubed, and b equals 5, that's the cube root of 125. You get 3 times the quantity 2x plus 3 times the quantity 4x squared plus 6x plus 9. For number 14, you have to think of x to the 4th as x squared squared, and think of x squared as x squared to the first power. So you can rewrite that as x squared squared minus 7 times x squared to the first power minus 8 equals 0. What some people do, instead of saying x to the 4th is x squared squared, they might say that x squared equals q, and then they would rewrite it instead as q squared minus 7q minus 8. They simplify it and then they substitute the x squared back in. This does the same thing. So I just rewrote this. Now is you have, in essence, you're going to use the same process as factoring a quadratic trinomial. So I need two numbers that multiply to -8 and add to -7. Those two numbers are +8 and -1. So you can rewrite this as x squared plus 8 times x squared minus 1 equals 0. Now, since we have an equation here and we're setting it equal to 0, we can take each factor and set it equal to 0, but we're not done factoring yet. X squared minus 1, because you have the difference of perfect squared, can be rewritten as x plus 1 times x minus 1. So, completely factored, x to the 4th minus 7x squared minus 8 becomes x squared plus 8 times x plus 1 times x minus 1, again, equals 0. Set x squared plus 8 equals 0. That means that x squared equals -8. You take the square root of both sides, and when you take the square root of both sides, you get a positive and negative root. So x equals positive negative square root of -8. We can take an I out. You get x equals positive and negative the square root of 8i. Square root of 8 can be simplified to 2 times the square root of 2. So let me take a deep breath. That becomes positive and negative 2 times the square root of 2i. Now for the other factors, you set x plus 1 equal to 0, subtract 1 from both sides, you get that x equals 1. And if x minus 1 equals 0, you add 1 to both sides and x equals 1. So when you're solving number 14, what you're going to do is you're going to say you have 4 solutions, which makes sense because you have an x to the 4th as your leading term. You have positive 2 square root of 2i. You have negative 2 squared root of 2i, which are your two imaginary solutions. And then your two real solutions in this case are x equals negative 1 and x equals positive 1.